So this is called trig form, trigonometric form of complex numbers. Yes, Ambry?
Yeah.
Only if you can go get me some popcorn from the concession stand.
I will do that.
All right.
Like just,
Okay.
I don't have any money, but I will get you some popcorn.
We'll turn the lights on. All right. So, trig form of complex number. So a complex number is something of the form a plus bi, right? Yes, ma'am. This is section 6-5, part A. So today, and when do I see you again? Wednesday. That's the only other day you're going to have to listen to me, okay? Today and Wednesday, and those are the last two sections of this chapter. So we're splitting section 6-5 into two parts, A and B. Yes, ma'am. Test is next block day. So we will review next Monday and next Tuesday, and then we'll take the test next Friday. Okay? Trig form of complex numbers, a plus bi. So when this is a complex number, we'll call it z. Sometimes they use this z. And this is the real part, and this is the imaginary part. And you've probably seen, you should have seen complex numbers last year. Did you?
I don't know.
Yes, you did. So a complex number might take the form 3 minus 2i, right? And so 3 would be the real part, and 2i would be the imaginary part, where I is equal to what? I is the square root of -1. And someone in the last class said, well, why do you have to have why do we need stupid imaginary numbers? Because they're just imaginary anyway, right? Well, mathematicians are very lonely, so they have to make up, they have imaginary friends, they have imaginary numbers, all that kind of. No, not really. But some of the higher level math, well, you've seen in factoring, sometimes you get imaginary roots, right? Which don't sit, and you can graph those imaginary roots in the imaginary plane, okay? And to solve some problems, sometimes there are only imaginary or complex answers, and sometimes the answer to a problem that involves multiplying two imaginary parts together will involve getting a real part. So just to make the mathematics work, they have complex numbers. But also I heard something on NPR when I wasn't listening to the Car Talk guys. I listened to them a lot. Anyway, but they had a good old thing, because someone asked this question, where do they use imaginary numbers in real life? And apparently there's a guy wrote a whole book about imaginary and complex numbers and all the math to do with that. But also in real life, I guess they use this to model like in wind tunnel testing and stuff. So if you want to figure out like the aerodynamics of a car, or an airplane or a jet or rocket or something like that, in aerodynamics they use imaginary numbers and modeling that kind of airflows and stuff, all that kind of stuff.
My dad uses imaginary numbers in his work.
He does?
Building, I don't know what it
What is he, like an aerospace engineer? Or?
Not space, but like computer-y stuff for
Yeah.
big companies.
Yeah, so
Circuit boards?
so they get building integrated circuits and stuff like that. Some of the properties of, I don't know, whatever they're called, resistors and trend, I don't know. But in any case, they do have some, even though they're imaginary, they do have some applications in real life. Okay, so so a number like this, like 3i, that's called a pure imaginary number. Shh, put your phone away, please. That's called pure imaginary, like 3i. And then a number like 2, that's called a real number, but it is a subset of a complex number. Like this can be written as 0 plus, this number can be written as 2 plus 0i, right? Likewise, this number can be written as 0 plus 3i. So even though this is a pure imaginary number, and this is a pure real number too, I can write them as complex numbers, and they're they're subsets of the complex numbers, right? So here's okay. I'm drawing. So here's complex numbers. Here's pure. I guess they would overlap, right? So here's pure imaginary. What? I'm drawing a Venn diagram.
Why is there a big circle?
Because that's all complex numbers.
Okay.
This is pure imaginary numbers. This is real numbers. And where they overlap, that would be something that's real and imaginary, which would be like 3 minus 2i would be in here. Okay. Anyways, okay. So you didn't like that? I'm gonna go away. Make it go away. Sorry, even though it was you guys made fun of me, so I'm getting rid of it. Okay. So you can graph. So sometimes it's very useful to graph complex numbers, and you can graph them in the imaginary plane. Okay. So this is the imaginary plane, and this is the imaginary axis. This one, the y-axis, is the imaginary axis, and this is the real axis. Okay, real axis, and this is imaginary axis. Imaginary axis. Okay, so if I wanted to graph a complex number like 3 plus 2i, I would go over 3, 1, 2, 3, and I'd go up 2 on the I-axis. So instead of this being y, it's I. So I would go over 3, up 2. I put a point there, and we kind of define these imaginary numbers as starting from 0, 0, originating as 0, 0, and going to that point. So they can be represented by a vector, okay, going from 0, 0 to that point. Okay? So that would be 3 plus 2i over there. Where would negative 2i be? Where would negative 2i be?
Just straight down.
Yes, ma'am.
So you graph it, it's a vector plus 2i? So it's supposed to have 2 arrows?
Yeah, it's ripped. Oh, there's not supposed to have 2 arrows on the end. Sorry. Go away. Sorry. So it's not supposed to have 2 arrows.
I'm sorry, those cylinders.
Not supposed to have 2 arrows on it. Only 1 arrow, and they're supposed to be green. Alright, so like that. Yeah. Represented by a vector. It's not really a vector, but it's represented by a vector.
Where's negative 2i?
Because the modulus, which we're going to talk about in a minute, it's the length, it's the distance from 0, 0 to that point.
So negative 2i is right here.
Yeah. What?
Why is I on the y-axis when I is on the x-axis?
Just to confuse you.
Just to confuse you. Okay? So, so negative 2i, come on. Negative 2i would be a vector going straight down 2 units, right? And so, not really a vector, but it would go from here to here. And the end point would be here at negative 2i. Where would how could I represent negative 5? Or I wrote negative 4. How could I write negative 5 in the complex plane? Plain old negative 5. Yes, sir. Just go left 5. 1, 2, 3, 4, 5. And there it is. And you could draw a vector to represent it going from there to there. Okay? This thing here, which we'll learn in a second, R, is called the modulus. I'll do another page because R is the length from 0, 0 to here, or the magnitude basically of the vector. And theta, this angle theta, that thing is called the argument. Okay? So theta again is going to be the angle from the x-axis to that vector representing the complex number. Okay? We'll talk about that in a second. Okay. Hold on. I gotta pause here. But I'm gonna talk at you for a while here. Here we're going again. All right. So the next thing is,
Wait,
uh-oh.
how do you spell modulus or whatever that
I'm
was?
gonna write it, okay?
Okay, that's good.
In a minute. So the absolute value of a absolute value of a complex number is just complex number is the distance between 0, 0 and AB and it's so the absolute value of A plus BI like this is equal to which is equal to the absolute value of Z if Z equals A plus BI. Okay? If Z equals A plus BI, which is equal to it's the same way as you find the magnitude of a vector. It's just the square root of A squared plus B squared. Okay? And let's see if there's anything I left out. So let's just do an example. So when they say find the absolute value, they're just talking about finding the magnitude. Okay? So find the abs value of -3 plus 2i. Z equals that. Oh, -3, sorry. I didn't mean to put an I there. -3 plus 2i. What's that equal to? All right, square root of -3 squared plus 2 squared, which is equal to the square root of 13. Questions? That's it. No I, because it's just it's really just the length of the vector that would connect that point to 0, 0.
Did you have a problem where you need to make it into a complex number to
Yeah, we're going to get there. We're going to get there. Yes, you would have a problem like that, Emily. So trig form. Look. I know. Okay. Trig form of a complex number. Luke, I am your father. Just kidding. I'm making a reference, you know that, right? Trig form. A complex number. So if I have a complex number Z, which is equal to A plus BI, trig form looks like this. Z equals R times cosine theta plus I sine theta, or you sometimes they write it like this: R cosine theta plus plus R sine theta I, okay, which is equal to that, where theta is called the argument, and R is called the modulus, and such that tangent of theta is equal to B over A, okay? And R is equal to, we already talked about that, A squared, square root of A squared plus B squared. Okay? So it's pretty much the same as with vectors, except it's a little bit different in that you have an I in there. Instead of it being x and y, it's x and I. But what's nice about in complex form, we have these formulas, and you can use those formulas to actually like raise 2 minus 5i to the 6th power. You wouldn't want to do that by hand, 2 minus 6i, and multiply 2 minus 6i, because you're going to get all kinds of imaginary numbers and stuff. But you could use these formulas to simplify, to raise complex numbers to powers and things like that. So in any case, there we go. So rewrite. So let's do this. Rewrite 2 minus 2 root 3i in trig form. In trig form. Okay? So the first thing you want to do is find r. So r is going to be the square root of a squared plus b squared. What's a? 2 squared plus negative 2 root of 3 squared. Okay, so r is equal to, whoops, I forgot to square that. What's 2 squared? 4. What's negative 2 root of 3 squared?
12.
Oh, you're a pretty smart kid, huh? Okay. 12. Do you see where Luke got 12 from? You see where Luke got 12 from? 2 squared is 4. Root of 3 squared is 3, right? And 4 times 3 is 12. Then I add them together and I get what? 16. And what's the square root of 16? 4. Okay, so that's 4. So that r value, it's always going to be a positive number, right? Now I got to find theta, which is a little more complex. Complex. So we know that tangent of theta is equal to b over a. So that would be negative 2 root of 3 over 2. But you have to be really careful. What's that equal to? Negative root of 3. Now, you can, so what you have to think here is you can't just take the inverse tangent of negative root of 3, because theta can be in the first quadrant, second quadrant, third quadrant, fourth quadrant. And it has to be an angle between 0 and 360, or 0 and 2 pi. Whereas if I take the inverse tangent, it has to be an angle between negative pi over 3 and pi over 3. The other thing is that tangent is negative root of 3 in 2 places. It's negative root of 3 down here when this is negative pi over 3, and it's also, whoops, it's also negative up here when this is 2 pi over 3, okay? So which one of these is it? So what is, where is this angle? In which where is this complex number? In which quadrant do I lie? In the fourth quadrant, okay? So I cannot call this negative pi over 3 because it has to be an angle between 0 and 2 pi. So I have to get to that angle going this way. Got it? And so what's that angle right there? If this is negative pi over 3 to get there, that would be?
300 degrees.
Yes, Emily?
How do you know you're in front?
Because it says go over 2 and down 2 root 3. Okay? That's I know. So I would call this angle 5 pi over 3. So you have to be really careful if it's not a positive angle, because you have to know which quadrant that angle is in.
How do you know?
How do I know?
Yeah.
By looking at where the original complex number is. So 2, it's over 2 down something, right? So that puts you in the fourth quadrant.
Oh, okay.
Okay? If it were back 2 and up 2 root 3, I'd still have the same inverse tangent, but it would be in the second quadrant. See? Yes, Avery? Because that's because when this angle is 60 degrees, tangent is negative root of 3.
Oh, okay.
Okay, so let's just rewrite it. So I'm going to rewrite it in complex form. It's going to go in trig form. So z is equal to r which I now know is 4, times the cosine of what? 5 pi over 3 times the sine or plus I sine plus I sine of 5 pi over 3. Okay? Okay, so this is what it looks like in trigonometric form. So 5 pi over 3 is the angle for both, right? Because that's the argument, 5 pi over 3. I sine of 5 pi over 3 gives you the vertical component, and cosine 4 times the cosine of 5 pi over 3 gives you the horizontal component. And you could distribute that 4 through if you want, either way is fine.
That's in trig form.
That's trig form, okay?
Oh, so that's rewriting 2 minus 2 root 3i in trig form.
Right. That's your final answer, yes. Now, don't always jump to doing all those steps. I'll come back, I'll post this on my website too, okay? Because sometimes if they say write z equals negative 3i in trig form, you could go through that whole process that I just went through, but sometimes it's useful. I would always draw a picture of things, okay? Because if I draw a picture of negative 3i, where is negative 3i? It's straight down, and it's on the x-axis. So if I went, whoops, I want to put arrows, one arrow. So if I went straight down 3 units, okay, if this is 1, 2, 3 units or something, okay, so this would be negative 3i. What's the angle from here to here?
270 degrees.
It'd be 270 degrees, right? Or 3 pi over 2 radians, right? What's the modulus? How long is this vector? It's just it's positive 3, right? The length of it is 3. So I could just rewrite this in complex form as 3 times the cosine of 3 pi over 2, or in trig form, plus I sine of 3 pi over 2. Where did I get 3 pi? Where did I get 3 from? Because the original complex number is just 3 straight down. Yes, ma'am.
Isn't it?
No, from here to here is 3 pi over 2. Okay? It could be Mitra, but then it would be wrong. That's not very nice. All right. So now you could go the opposite direction. Oh, I have 5 more minutes and I talked too much, okay? So 5 more minutes, and I didn't teach you everything. I'll let you worry about, well, real quick, right? In standard form.
Wait, standard form is like a plus.
Yeah, a plus bi form. So if you have something like this, square root of 5 times the cosine of 5 pi over 6 plus I times the sine of 5 pi over 6. All you do is you just simplify this out. So root of 5, since I'm in a rush, I'm going to tell you that the cosine of 5 pi over 6 is negative root of 3 over 2. And the sine of 5 pi over 6, anyone know real quick? Positive 1/2. So when I simplify this, okay, there should be brackets around this, I get negative 15, negative square root of 15 over 2 plus I root of 5 over 2. Okay? Okay, now we have these formulas that I have to give you, and if I don't get to them, you're going to have to watch my video or look in the book. They're pretty easy, but don't go away yet. You have 2 complex numbers. So if I have z1 equals r1 cosine theta 1 plus I sine theta 2. And z2 equals r2 cosine theta 2 plus I sine theta 2. Then it holds that. Whoops. Oh, sorry. This should have been a 1. I'm sorry. Okay? Then z1, if I want to multiply two complex numbers in trig form, it's equal to, z1 times z2, it's equal to r1 times, not dot product, but times z cosine of theta 1 plus theta 2 plus I sine of theta 1 plus theta 2. And with division, z1 divided by z2 is equal to r1 divided by r2 times z cosine of theta 1 minus theta 2. Well, I'll show you in a minute, a really quick example. So this is really easy, but you got to know what they're talking about. Theta 1 minus theta 2, okay? So if z1, watch. Times. If z1 is equal to 8 cosine 120, hold on, let me finish. I sine 120, and z2 is equal to 6 cosine 150 plus I sine 150. One more second. Then z1 times z2 is equal to 8 times 6 times the cosine of the sum of these two, which is 270, plus I sine of 270. So you multiply the moduli, and you add together the angle. And then you could simplify that as well. Okay? But your homework's on my website. Sorry I ran out of time. I shouldn't tell.